Laplace transform for ramp function. Normally ramp function can be denoted like this: ramp function r of t. So it is denoted like this. T, it is r of t. So this is the slope of this curve is a. A is the slope of this curve. Now r of t, this can be defined as is equal to 0 for t less than 0. For t less than 0 it is 0. For t greater than 0 it is a straight line equation, and that equation is at. It is for t greater than 0. So we can define this r ramp function like this. Now the Laplace transform for r of t is equal to integral 0 to infinity r of t into e power minus st dt. Here 0 to infinity, that means t greater than 0. 0 to infinity, it is at e power minus st dt. A is constant, we can take it out from this integration. So a into integral 0 to infinity t e power minus st dt. So it is a into, it is like integral 0 to infinity x power n e power minus x dx. The formula for this one is gamma of n plus 1. We already discussed this one. Gamma of n plus 1 is n factorial. So now let me write this expression in this form. To write that expression in this form, I am assuming that st is equal to some x. St is equal to x. Now t is equal to x by s. Now substitute here, if t is equal to 0, x is equal to 0. T is equal to infinity, x is also infinity. The limits are same for this integration. So write it a into integral 0 to infinity. In place of t, write this x by s. And from this dt is equal to 1 by s into dx. You substitute this t, in place of t it is x by s, e power st place, in place of st that is x, and dt is equal to 1 by s into dx. S is constant, I can take it out from this integration. So a by s square, and it is 0 to infinity x e power minus x dx. Here the value of n in this formula, the value of n here is 1. So it is n plus 1 gamma of n plus 1, that is gamma of 2, that is 1 factorial. So a divided by s square into 1 factorial. The value of 1 factorial is 1. So it is a by s square. So finally Laplace transform for ramp function is a by s square, where a is the slope of that curve. Next, Laplace transform of delayed ramp function. Delayed or shifted ramp function. Delayed or shifted ramp function. So this delayed or shifted ramp function can be denoted as r of t minus a. So this can be represented like this. Graphical representation of this delayed or shifted ramp function will be like this. It is a function, delayed ramp function r of t minus a. It is t, and it will start from this point, that is a. Okay, and this can be defined as, this shifted or delayed ramp function can be defined as r of t minus a is equal to 0 for t less than 0. for t less than a here, for t less than a it is 0, and for t greater than a it is t minus a. It is not t, it is t minus a. Sorry, the slope of this curve, let us assume, is a, and this is a into t minus a, a into t minus a. So let me write, so for this for t greater than a it is a into t minus a. So now see, if you want to find this expression, let us take this as this point, this y quantity is 0, x quantity is a, so a comma 0, this point is a comma 0, and the slope of the curve is a. If I know one point and the slope, I can find the straight line equation. That expression here is y minus y1 is equal to m into x minus x1. So x1 comma y1, these are the points here. X1 is a, y1 is 0, and slope is a here. So y means it is y-axis. In y-axis I am taking r of t minus a, r of t minus a, minus y1 is 0 here. Here m is slope a, x is t here, t, minus t1, x1 is a here. Okay, so r of t minus a is equal to a into t minus a. So for t greater than a, r of t minus a is equal to a into t minus a. Now I need to find the Laplace transform for this delayed or shifted ramp function, that is Laplace transform of r of t minus a. So to find this, I am using this Laplace transform formula, that is 0 to infinity r of t minus a into e power minus st dt. And from 0 to a, that means for t less than a, the value of r of t minus a is 0. So if I split this integration, it will become 0 to a r of t minus a into e power minus st dt plus integral a to infinity r of t minus a into e power minus st dt. So this term, this value is r of t minus a is from 0 to a, that means for t less than a, that the value of r of t minus a is 0. So this value is 0. So this integration will become 0, 0 plus this one, integral a to infinity r of t minus a is, so for t greater than a, r of t minus a is a into t minus a. So it is a into t minus a e power minus st dt. Now if you solve this expression, so it is integral so a is constant, I can take it out from this integration, a into integral a to infinity t into e power minus st minus a into, it is constant a, integral a to infinity, so it is dt, a to infinity e power minus st dt. And this one, so this integration I am going to find now. The formula for integral uv is u integral v minus integral u dash integral v. So here let us consider this is u and this is v here, because Liet logarithmic function, inverse trigonometric, algebraic, trigonometric, exponential. So exponential function is the last one, so it is v. So algebraic function is before that, so that is u. First one is u, second one is, after that last one is v here. So now, so let us use this formula to find this value, a into this value u is t, integral v, I need to integrate this one. If I integrate e power minus st, it will be with respect to t here, e power minus st by minus s, and substitute the limits here, or the limits from a to infinity, so it is a to infinity minus integral. So what is this integration value? A to infinity u dash value is, if I integrate t here, sorry, if I differentiate t here, so that will be 1. Integral v, so if I integrate this one, it will become e power minus st by minus s dt. Anyway, this integration is minus a into, for this one, so if I integrate this one, e power minus st divided by minus s, and the limits for this one are a to infinity. For this total one, it is a. Right. Now it is substitute here a into, if I substitute these limits here, e power minus infinity. The value of e power minus infinity is 0. So it is 0. If I substitute the upper limit, it will become 0. Minus, if I substitute a in place of t, so it is a into e power minus as divided by minus s. Just I am substituting these limits in this expression, in this equation. Now it is minus and minus, it is plus. So if I integrate this one, e power minus st by, if I integrate the e power minus st, then it will be e power minus st is 1 by s. Minus and plus, minus and minus, it is plus here, 1 by s, e power minus st divided by minus s, and the limits here are a to infinity. Minus and minus here, it is plus, so it is a by s. So I can take it out from this limits. So if I substitute infinity here, e power minus infinity is 0, minus, if I substitute a here, e power minus as. Okay. Now it is minus and minus, it is plus, so a into e power minus as divided by s plus 1 by s into, if I substitute minus into plus, here it is minus 1 by s square. If I substitute infinity in this in this place of t, e power minus infinity is 0, minus, if I substitute a in place of t, it will be e power minus as, plus into minus, it is minus a into e power minus as divided by s. So this minus into minus a into e power minus as by s, this one will get cancelled. So finally what we got here is, it is minus and minus plus here, so it is a into e power minus as divided by s square. So finally the Laplace transform for this shifted or delayed ramp function is this one. Next, impulse function. So before going to that, if you want to find the delayed or shifted ramp function Laplace transform, sorry, if you want to find unit shifted ramp function Laplace transform, if you want to find the Laplace transform for shifted unit ramp function, then in this place a value is 1. So that is equal to, if a substitute a is equal to 1, e power minus as divided by s square. So this is the value for shifted unit ramp function. Next thing here is unit impulse function. Impulse function Laplace transform. Normally this impulse function is denoted as delta of t. So the graphical representation of this impulse function is like this. So it is t, it is delta of t. and the value of delta of t will exist only at t is equal to 0. So this point is at t is equal to 0. That means this delta of t can be defined as delta of t is equal to, it is 1 or a, it is a for t is equal to 0, and for t not equal to 0, that means in this place, the value of delta of t is 0. For unit impulse function, the value of a here is 1. Okay, and also in this minus infinity to infinity, if I integrate this delta of t from minus infinity to infinity, this value will become 1. And the Laplace transform for delta of t is, if it is not a unit impulse function, then it is a. For unit impulse function, Laplace transform of delta of t is equal to 1. Next one is exponential function. Exponential function, that is e power at. The Laplace transform for exponential function e power at is 1 by s minus a. I am going to derive this expression here. So just you use this formula to prove this expression. So 0 to infinity f of t, here is f of t is e power at, e power minus st dt. So here bases are same, then I can write this expression as 0 to infinity e power at minus st dt. So I can write this one as integral 0 to infinity e power so here it is, if I write this expression a minus s into t dt, the integration for e power ax here is e power ax divided by a. So e power a minus s into t divided by a minus s, and the limits here are 0 to infinity. Substitute, just if you take the common minus sign here, so it will become 1 by a minus a into e power minus s minus a into t. The limits here are 0 to infinity. So here 1 by a minus s into, if I substitute infinity here, e power minus infinity is 0. If I substitute 0 here in place of t, e power 0 is 1. So it is minus 1 divided by a minus s. If I take negative side in this denominator, then it will become 1 by s minus a. So the Laplace transform for e power at is this one. So it is the Laplace transform for exponential function. Next for sine function, I think it is the 8th one. Next 9th one is sine function. For sine function, what is the Laplace transform? Laplace transform of sine omega t is equal to omega divided by s square plus omega square. So this formula I am going to prove here. Know that sin omega t is equal to, I can write it as 1 by 2i e power j omega t minus e power minus j omega t. So this is the formula, 1 by 2j here. j means I here, so 1 by 2j into e power j omega t minus e power minus j omega t. Okay, so Laplace transform for sin omega t is equal to 1 by 2j. So the Laplace transform for e power j omega t minus e power minus j omega t. So it is equal to 1 by 2j. The Laplace transform for e power at, just now we discussed, that is 1 by s minus a. So it is 1 by s minus j omega. The Laplace transform for this one also 1 by s plus j omega. Here a is minus j omega. Here a is plus j omega. So it is 1 by 2j. If I find this one, a s plus j omega minus s minus j omega divided by s square minus j omega whole square. So it is 1 by 2j. This s and this s will get cancelled, minus into minus plus. So it is 2j omega divided by, so it is a j square into omega square. J square is minus 1. So minus into minus, it is plus. So s square plus omega square. So this 2j plus 2j will get cancelled here. So finally we got omega divided by s square plus omega square. So this is the Laplace transform for sin omega t. Next thing here is Laplace transform for cosine function. 10th one, cosine function. Cos omega t. So the Laplace transform for this cos omega t is s divided by s square plus omega square. Here Laplace transform of cos omega t is equal to, normally cos omega t we can write the formula for cos omega t is 1 by 2 into e power j omega plus e power minus j omega. So sorry, it is j omega t, e power minus j omega t. So this is the formula for cos omega t. So if I apply the Laplace transform for this cos omega t, so it is equal to 1 by 2 into Laplace transform of e power j omega t plus e power minus j omega t. So that is equal to, so the Laplace transform for this e power at is 1 by s minus j omega plus 1 by s plus j omega is equal to 1 by 2 into, so if I find these fractions, s minus j omega divided by s square, it is plus omega square. J omega will get cancelled, so it is 1 by 2 into 2s divided by s square plus omega square. This one will get cancelled. So finally Laplace transform for cos omega t is equal to s divided by s square plus omega square. Next, hyperbolic functions. 11th one is hyperbolic sine function. That is sine h omega t. So for this hyperbolic sine function, Laplace transform of sine h omega t is equal to, it is omega divided by s square minus omega square. It is for sine omega t, Laplace transform is omega divided by s square plus omega square, but sine h omega t, it is omega divided by s square minus omega square. So let me derive this. For that the formula is required for sine h omega t is equal to 1 by 2 into e power omega t minus e power minus omega t. Sin omega t formula is 1 by 2j into e power j omega t minus e power minus j omega t, but sin h omega t formula is this one. If you apply Laplace transform for sin h omega t, so this is equal to 1 by 2 into Laplace transform of e power omega t minus e power minus omega t. So the Laplace transform for this one is 1 by s minus omega minus 1 by s plus omega. So that is equal to 1 by 2 into s plus omega minus s minus omega divided by s square minus omega square. So this s and this s will get cancelled, minus of minus it is plus. So 1 by 2 into 2 omega divided by s square minus omega square. These 2 and these 2 will get cancelled. So finally Laplace transform for sin h omega t is equal to omega divided by s square minus omega square. Next, hyperbolic cosine function. Twelfth one is hyperbolic cosine function, that is cos h omega t. So for this, the Laplace transform of cos h omega t is equal to, it is s divided by s square minus omega square, and the proof for it is cos h omega t formula here is 1 by 2 into e power omega t plus e power minus omega t. So if you apply the Laplace transform, cos h omega t is equal to 1 by 2 Laplace transform of e power omega t plus e power minus omega t. So it is 1 by 2 into 1 by s minus omega plus 1 by s plus omega. So it is 1 by 2 into, it is s plus omega plus s minus omega divided by s square minus omega square. This omega and this omega will get cancelled here. So it is 1 by 2 into 2s divided by s square minus omega square. This 2 will get cancelled here. So Laplace transform for cos h omega t is equal to s divided by s square minus omega square. Next, exponentially damped function. Exponentially damped function. So this can be represented as e power minus at f of t. Damping means reducing the oscillations. So it is e power minus at into f of t. For this, I need to find the Laplace transform. If Laplace transform of f of t is equal to f of s, then Laplace transform of e power minus at f of t is equal to f of s plus a. I am going to prove this one. Here Laplace transform of e power minus at f of t is equal to integral 0 to infinity e power minus at f of t to e power minus st dt. Here this is a function, this one. So integral 0 to infinity f of t, these bases are same here, so I can add this these powers here, s plus a into t dt. So if I take the negative sign, so it will become this one, and in place of s it is s plus a. What is the Laplace transform of f of t? Is equal to integral 0 to infinity f of t into e power minus st dt. But in place of s it is s plus a. All are same here except this, all are same here. So it is equal to f of s actually. in place of s, here it is s plus a, so this will be f of s plus a, this one will be f of s plus a, that is Laplace transform of e power minus at f of t, this one. Next thing here, properties of Laplace transforms. So properties of Laplace transforms. So in this the properties that we are going to discuss here are, one is linearity property, second one is time scaling property, third one is time shifting property, fourth one is frequency shifting property, frequency shifting property. I think there are 10 properties are there. Fifth one is multiplication with t, this property, division by t, this property. So another one, time differentiation property, differentiation property. Next, eighth one is time integration property. Ninth one is initial value theorem. And one is final value theorem. So these are the properties that I am going to discuss. So in these properties, these two are important. This initial value theorem and final value theorem are important. So let me discuss one by one here. First one, linearity property. What it says here is, if Laplace transform of f1 of t is equal to f1 of s and Laplace transform of f2 of t is equal to f2 of s, then Laplace transform of a into f1 of t plus b into f2 of t is equal to a into f1 of s plus b into f2 of s. So this is the linearity property. Let me get the proof for this. So Laplace transform of a into f1 of t plus b into f2 of t. So I can write it as this one. It is integral 0 to infinity a into f1 of t plus b into f2 of t. It's a function into e power minus st dt is equal to, so I can split this integration like this: a into integral 0 to infinity f1 of t dt plus b into integral 0 to infinity f2 of t, f1 of t, this e power minus st also. Okay, let me this e power minus st. Now multiply with this one, a into integral 0 to infinity f1 of t into e power minus st dt plus b into integral 0 to infinity f2 of t into e power minus st dt. So this is the formula for Laplace transform of f1 of t, and this is the formula for Laplace transform of f2 of t. So Laplace transform of f1 of t is a into f1 of s plus b into f2 of s. So this is the proof for linearity property. Second one is time scaling property. Second one is time scaling property. Time scaling property. So what is this time scaling property here is, if Laplace transform of f of t is equal to f of s, then Laplace transform of f of at is equal to 1 by a into f of s by a. So this is the time scaling property of Laplace transforms. Let me derive the proof for it. So Laplace transform of f of at is equal to integral 0 to infinity f of at e power minus st dt. Here put at is equal to some x. Now for t is equal to 0, this limit I am going to calculate. What is the value of x here? X is also 0. For t is equal to infinity, what is the value of x? X is equal to infinity. And from this, if you find the value of dt, that is equal to 1 by a into dx. From this, let us substitute all these values in this. So that is equal to Laplace transform integral 0 to infinity. In place of at, substitute x here, f of x e power minus s into, in place of t, x by a. So it is x by a dt, it is 1 by a into dx. Now it is integral 0 to infinity f of x, it is 1 by a here. I can write as e power minus s by a into x dx. Now it is like it is 1 by a into, it is like the formula for integral 0 to infinity f of t e power minus st dt is equal to f of s. We know that. In place of t, here it is x, and in place of s, here it is s by a. So I can rewrite this expression like this: 1 by a into f of s by a, it is f of s by a. So Laplace transform of f of at is equal to 1 by a into f of s by a. Here the next one is time shifting theorem. Third one here is time shifting theorem. So what this time shifting theorem says here is, if Laplace transform of f of t is equal to capital F of s, then Laplace transform of f of t minus a, time shifting, is equal to e power minus as into f of s. So I am going to prove this. To prove this, I am using the bilateral Laplace transform. What is meant by bilateral Laplace transform here is, Laplace transform of f of t is equal to integral minus infinity to infinity f of t to e power minus st dt. For unilateral Laplace transform, it is from 0 to infinity. It is bilateral Laplace transform. So I am using this bilateral Laplace transform to prove this time shifting theorem. Now let me write this Laplace transform f of t minus a. f of t minus a is equal to minus infinity to infinity f of t minus a e power minus st dt. Now let me write some x is equal to t minus a. In place of t minus a, replace with x. Suppose t limit here is, for t is equal to minus infinity, x is equal to minus infinity. For t is equal to plus infinity, x is equal to plus infinity. The limits are same here. So this integration I can read it as integral minus infinity to infinity. In place of t minus a, replace with x, f of x. In place of t, what is t here? X plus a, and dt is equal to dx if I differentiate this one. So e power minus s into t value is x plus a, dt value is dx, is equal to integral minus infinity to infinity f of x e power, if I split this, e power minus sx into e power minus as into dx. If I take this common, e power minus as into integral minus infinity to infinity f of x dx. So e power it is f of x e power minus sx dx. So this one is like this one, except in place of t here it is x. So I can write as, what is this, f of s. So it is e power minus as into, this is also same, only the variables are changes here. Here it is t, here it is x. So this will become f of s. So Laplace transform for f of t minus a is equal to this one. It is time shifting theorem. Next one is frequency shifting theorem. Frequency shifting theorem. Okay. So in this, what this frequency shifting theorem says here is, Laplace transform of, if Laplace transform of f of t is equal to f of s, then Laplace transform of e power minus at f of t is equal to f of s plus a. So this is nothing but the frequency shifting theorem. So let me prove here. Laplace transform of e power minus at f of t is equal to integral, I can use this unilateral Laplace transform here. Only for this time shifting theorem I am using this bilateral Laplace transform. We can also use the unilateral Laplace transform, but it will become very difficult to there is a complex calculations will be there. So to avoid this problem, I am using this bilateral Laplace transform here. Here I am using the unilateral Laplace transform here, 0 to infinity. Here this function is e power minus at into f of t. Here it is e power minus st dt. Now I can write it as 0 to infinity f of t into, this bases are same, so I can add this powers s plus a here, this s plus a t into dt. So in place of s it is s plus a, so it is f of s plus a. So Laplace transform of e power minus at f of t is equal to this one. It is the frequency shifting theorem. Next, fifth one is multiplication by t. So fifth one is multiplication with t. So what it is saying here is, if Laplace transform of f of t is equal to f of s, then Laplace transform of t into f of t is equal to minus d by ds of f of s. I am going to prove it. Laplace transform of t into f of t is equal to integral 0 to infinity t into f of t e power minus st dt. Here if I proceed like this, then I cannot find the value of this Laplace transform t into f of t. So I am going to proceed in a different manner. Laplace transform of f of t is equal to f of s. You know this. Differentiate this d f of s divided by ds with respect to s. And here Laplace transform of f of t is integral 0 to infinity f of t e power minus st dt, that is equal to f of s here. So df of s by ds, if I differentiate this one, d by ds of integral 0 to infinity f of t e power minus st dt, that is equal to, if I bring this differentiation into the integration, it will become dou by dou s. Here the two variables are there, t and s. So partial differential equation I need to use here. 0 to infinity f of t dou by dou s of e power minus st dt. So differentiate this e power minus st with respect to s here, then I will get 0 to infinity f of t. If I differentiate it, e power minus ax, it is minus a into e power minus ax, it is minus a into dt here. Sorry, with respect to s here, so it is minus t. Here a value is this one. A value here is e power minus ax, a value here is t. So it is this one. Now integral, it will become integral 0 to infinity minus, take this minus sign out of this integration, t into f of t e power minus st dt. What is this? It is d f of s by ds. And this expression, if I assume this is a function, it will become Laplace transform of t into f of t minus of. So it is d f of s by ds. Now Laplace transform of t into f of t, if I bring this negative sign to this left side of that equation, minus d f of s divided by ds. This is how we need to prove this multiplication with t. Next, division with t. Sixth one is division with t, division by t. So what it says here is, if Laplace transform of f of t is equal to f of s, then Laplace transform of f of t by t is equal to integral s to infinity f of s. So this is division by t Laplace transform property. S to infinity f of s ds, it is ds here. So the procedure is same as that of this one. Instead of differentiation, I am doing the integration here. Laplace transform of f of t is equal to f of s. And what is this Laplace transform of f of s is equal to, now this is Laplace transform of f of t, I can write it as 0 to infinity f of t e power minus st dt. And apply the integration on both sides with these limits s to infinity. Integral s to infinity f of s ds, integral s to infinity, integral 0 to infinity f of t e power minus st dt. Now first you apply the integration for this this integration. First you apply this integration, after that you apply this integration. Just interchanging these integrals here, 0 to infinity f of t. Now function of s here is s to infinity e power minus st dt. Here it is ds. It is ds. So integral 0 to infinity f of t. If I find this integration, it is e power minus ax, a value here is t, so it is minus e power minus ax divided by minus a. The limits are s to infinity, it is dt. Now it is integral s to infinity f of s ds is equal to integral 0 to infinity. It is integral 0 to infinity. What is this f of t? Here it is minus 1 by t. Apply this limits here. In place of t, if I apply infinity, upper limit e power minus infinity is 0. If I apply in place of s, I need to put this infinity, because with respect to s I am integrating this one. So in place of s, if I substitute infinity, it is e power minus infinity is 0. In place of s, if I substitute s, it will become e power minus st dt. It is dt. Now it is integral 0 to infinity minus f of t by t. So this minus and this minus will get cancelled here, so it is plus minus minus, so it is e power minus st dt. And this I can write as Laplace transform of f of t by t. So the Laplace transform for f of t by t I can find by integrating this f of s with the limits s to infinity. So this is the property of division by t. Next, seventh property here is time differentiation. Time differentiation. Time differentiation theorem or time differentiation property. What it says here is, if Laplace transform of f of t is equal to f of s, then Laplace transform of f dash of t. F dash of t is, here f dash of t is d by dt of f of t. So Laplace transform of the derivation of f of t here is s into f of s minus f of 0. Laplace transform of f double dash of t is equal to s square into f of s minus, here it is s into f of 0 minus f dash of 0. Similarly, etc. Laplace transform of nth derivative of f of t is equal to s power n into f of s minus s power n minus 1. This s powers will be reducing, s power n minus 1, s power n minus 2, finally s power 0. So here it is s power n minus 1 f of 0 minus s power n minus 2 f dash of 0 minus s power n minus 3 f double dash of 0 minus dash 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 s into f power n minus 2 of 0 minus f power n minus 1 of 0. So this is the theorem, time differentiation theorem. So this I am going to prove here. Laplace transform of f dash of t is equal to integral 0 to infinity f dash of t e power minus st dt. So it is like integral uv formula. I am applying integral uv, u integral v minus integral u dash integral v. This is the formula. So here let us take, so v is this one and u is this one, because if I apply the integration it will be differentiation, integration will get cancelled. So u is e power minus st, integral v is integral 0 to infinity v f dash of t dt minus this integral u dash. If I differentiate this one with respect to t, so it is e power minus st into minus s 0 to infinity. V is this one, integral 0 to infinity f dash of t dt. So for this one, for this total one, it is dt. Now it is e power minus st. This differentiation and this integration will get cancelled here, so it is f of t, and the limits here are 0 to infinity minus integral 0 to infinity, this minus and this minus will be plus s into this integration and this differentiation will be cancelled here, s into f of t into e power minus st dt. Here this s is constant, it is not the function of time here, so I can take it out from this integration. Substitute this upper limit here, e power minus infinity is 0 minus this one. If I substitute a lower limit here, e power 0 is 1 into f of 0, so it is f of 0 plus s, I can take it out from this integration, 0 to infinity f of t e power minus st dt, and we know that it is the Laplace transform for f of t. Laplace transform for f of t is f of s, so substitute here, it is f of s. So this will be s into f of s minus f of 0. So this is the Laplace transform for f dash of t. Similarly, you find the Laplace transform for f double dash of t. So this f double dash of t, I can write as Laplace transform of d by dt of f dash of t. It's a function. Let us assume f dash of t is some x of t. So here Laplace transform of x dash of t I need to find. X of t is f dash of t. Again I need to differentiate this one, so it is x dash of t. So what is the Laplace transform of x dash of t? Just now we discussed this is for f dash of t, it is s into f of s, instead of s, f, it is x of s minus x of 0. Now I need to find this x of s, that is x of s is Laplace transform of x of t, that is Laplace transform of x of t is f dash of t. Laplace transform of f dash of t is that we calculated s into f of s minus f of 0. So you substitute this x of s in this expression. So x dash of t is, finally x dash of t is nothing but f double dash of t, that is equal to s into x of s. S into x of s is this one, s into f of s minus f of 0 minus x of 0. So multiply this, s square into f of s minus s into f of 0 minus x of 0. X of 0 is here, if I substitute t is equal to 0 here, x of 0 is equal to f dash of 0. So it is f dash of 0. So Laplace transform of f double dash of t. So similarly, if you go on like this, Laplace transform of f power n times of n time differentiation of f of t is equal to s power n into f of s minus s power n minus 1 into f of 0 minus s power n minus 2 into f dash of 0, like that. S into, it means f power 1. It means if you calculate it, n minus 2 plus 1, here it is n minus 1. So here it is n minus 2 of 0. The powers will be n minus 1, common here, n minus 1, like that, minus f power n of n minus 1 of 0. So this is the formula, and it is a proof for time differentiation theorem. Next thing here is time integral theorem or time integration theorem. That is the 8th one, time integration theorem. 8th one is time integration theorem. What it says here is, if Laplace transform of f of t is equal to f of s, then Laplace transform of integral 0 to t f of t dt, that is equal to f of s divided by s. This is what I am going to prove now. Time integral theorem. So to prove this, apply Laplace transform of integral 0 to t f of t dt is equal to, its total thing is a function. So integral 0 to infinity, the definition of, according to the definition of Laplace transform. So this function here is integral 0 to t f of t dt e power minus st dt. Two integrations are there here. So again I am going to apply integral uv rule here. Uv, integral uv is equal to u integral v minus integral u dash integral v. So here which one is u and which one is v? So u dash, if I take this one as a u dash will become f of t here. So I am going to take this one as u and this one as v here. So u is, here it is 0 to t f of t dt into integral v. If I find the integration for it with respect to t, I need to integrate e power minus s divided by minus s, and the limits are 0 to infinity. So the limits are from 0 to infinity, minus integral u dash. So I need to differentiate this one. If I differentiate this one, it will become f of t. Integration and differentiation will get cancelled. Finally it is 0 to infinity. This one is 0 to infinity. This integration is 0 to infinity. U dash is, if I differentiate this one, integration and this differentiation will get cancelled. So it is f of t. Integral v. So again I need to, this one has to be integrated. So it is e power minus st by minus s. It is with respect to dt, with respect to t here. So now let me take this out of this integration. In place of t, if I place infinity, upper limit, if I substitute upper limit here, so it is minus 1 by s. Take this out of this integration, out of this limits also. Integral 0 to infinity f of t dt into e power minus infinity. So it is in place of t I am substituting this one, 0 to infinity, t is infinity, f of infinity into dt to e power minus infinity, minus 1 by s. Anyway it is taken out. So if I substitute this upper limit, it will be like this, minus if I substitute 0 here, integral 0 to 0, 0 to 0, f of 0, it is dt, e power 0, if I substitute here, that is 1, minus into minus, it is plus, integral 0 to infinity, 1 by s taken out, 1 by s, f of t e power minus st dt. Now this e power minus infinity value is, it is 0. From 0 to 0 there will not be any function, f of 0 is 0, so this total function also 0. So this value is 0, this value is 0. Finally what we got here is only this one, that is 1 by s into, this is Laplace transform of f of t, that is equal to f of s divided by s. So finally Laplace transform of integral 0 to t f of t dt is equal to f of s divided by s. It is time integral theorem. Next thing here is initial value theorem. Initial value theorem. So what this initial value theorem says here is, if Laplace transform of f of t is equal to f of s, then limit t tends to 0, f of t is equal to limit s tends to infinity, s into f of s. This is the initial value theorem. How I am going to prove this? You see here, it is important theorems, initial value theorem and final value theorems. So I am taking this expression to prove this initial value theorem. Laplace transform of f dash of t is equal to s into f of s minus f of 0. From this, s into f of s is equal to Laplace transform of f dash of t. So it is integral 0 to infinity f dash of t into e power minus st dt. If I bring this f of 0 to the left side of the equation, it will become plus f of 0. Now apply the limits here. Limit s tends to infinity, limit s tends to infinity, s into f of s. Apply the limits on both sides of this equation. So it is limit s tends to infinity, integral 0 to infinity f dash of t e power minus st dt plus f of 0. So if I apply the limit s tends to infinity, for this there is no s term here, so as it is, whatever this one will be reflected here, that is plus f of 0. Now this limit, if I bring this limit into the integration, and if I put in place of s infinity, e power minus infinity, e power minus infinity value is 0, so it is, or otherwise you substitute here 0 to infinity f dash of t into e power s tends to infinity, e power infinity dt plus this one. So e power minus infinity is, this value is 0, so 0 plus f of 0, and this is limit s tends to infinity s into f of s. So this can be, I can write it as limit t tends to 0 f of t. So this is the initial value theorem. Next let me explain the final value theorem. This can also be the, we can also the prove this final value theorem same as that of the initial value theorem. Last one, that is final value theorem. Final value theorem. In this final value theorem, what it says here is, if Laplace transform of f of t is equal to f of s, then final value, that is limit t tends to infinity, final value f of t is equal to limit s tends to 0 s into f of s. The same thing, the same procedure I am going to follow here to prove this. So use this Laplace transform of f dash of t is equal to s into f of s minus f of 0. Now s into f of s is equal to, if I bring this term to the left side, then it will become, apply this Laplace transform, integral 0 to infinity, this function is f dash of t into e power minus st dt, this plus f of 0. Apply limit s tends to 0 s into f of s. Here limit s tends to 0, integral 0 to infinity f dash of t to e power minus st dt plus f of 0. Now limit, if I bring this limit into the integration, f dash of t is s tends to 0. If I replace this s with 0, e power 0 dt plus f of 0. This integration and differentiation will get cancelled, so it will become f of t, and the limits are 0 to infinity plus f of 0. Here put this upper limit here, so it is f of infinity minus, now lower limit minus f of 0, so it will become f of 0. This f of 0, this f of 0 will get cancelled, so finally I got here is f of infinity. So this one has limit t tends to infinity f of infinity. So this is limit s tends to 0 s into f of s. So this is the final value theorem. So this is how we can prove this final value theorem. So these are the properties of this Laplace transforms.